A gemstone worth thousands, mistaken for a dull river pebble. No sparkle, no vivid color, no reason to stop and look twice. Just a small, weathered stone moving quietly through shallow water, surrounded by countless others that appear identical. Yet inside some of these unremarkable minerals exist crystal structures formed under conditions so rare, they occur in only a few places on Earth. Subtle green revealed only after cutting, fire hidden inside cloudy rough, color that shifts only when light hits from the right angle. Nothing about them looks valuable at first glance, until the moment they are finally understood. Starting with number 10, a gemstone often ignored because its surface reveals almost nothing about what lies within. Ranked 10th, zircon. Most stones that attract attention in riverbeds do so immediately. They reflect light, they display color, they signal difference. Zircon rarely does. When found in alluvial environments, zircon crystals are often rounded by water movement, their edges softened over time as they travel through sediment systems. Surface abrasion gradually removes the visual cues that might otherwise distinguish them from surrounding material. Instead of appearing exceptional, many zircon fragments take on the quiet appearance of ordinary pebbles. Muted tones, weathered surfaces, and no obvious sign of internal optical potential. For local miners working within river deposits, attention typically shifts towards stones that display immediate transparency or noticeable color zoning. Zircon, in contrast, often presents itself without urgency. Its exterior can appear subdued, sometimes cloudy, sometimes brownish, occasionally resembling fragments of quartz or common silicate minerals that frequently populate the same geological environments. Yet internally, zircon possesses a refractive index significantly higher than many more recognized gemstones. Once cut, its optical behavior can produce a level of brilliance that surprises even experienced collectors encountering the material for the first time. The difference between rough zircon and faceted zircon is not subtle, it is structural. The challenge lies in the fact that zircon rarely announces this potential during the earliest stages of discovery. Without careful observation, the stone may simply blend into the background of thousands of similar-looking fragments carried downstream over long geological timescales. Historically, zircon has been present in river gravels across multiple continents, transported far from its original host rock. In these environments, visual distinction becomes difficult. Size, color, and surface texture often overlap with more common minerals, reducing the likelihood of immediate recognition. Only after cleaning, examination, and cutting does zircon begin to reveal the optical characteristics that define its value. Dispersion and brilliance emerge gradually, transforming what once appeared unremarkable into a gemstone capable of strong light performance. Zircon demonstrates a recurring pattern observed throughout mineral exploration. Rarity does not always appear rare at first glance. In riverbeds shaped by erosion and time, value can remain visually quiet, present but easily overlooked when expectations favor immediate visual distinction. Zircon's understated appearance makes it an ideal starting point for understanding how high-value gemstones can remain hidden in plain sight, waiting for recognition that does not rely on surface impressions alone. Ranked 9th, Andalusite. Some gemstones do not reveal their identity in the environment where they are first discovered. They require change. Andalusite is one of the clearest examples of how transformation can separate appearance from value. In natural conditions, rough Andalusite often displays subdued tones that blend easily with surrounding material. Brownish, olive, or muted green fragments may appear visually indistinct when transported through river systems shaped by erosion. Rounded edges, surface wear, and sediment staining can further reduce contrast between Andalusite and more common silicate minerals found in the same geological settings. To an untrained observer, a water-worn piece of Andalusite may not appear significantly different from countless other stones occupying the same gravel bed. Yet Andalusite possesses a property that is rarely obvious in rough form: strong pleochroism. This optical behavior allows the gemstone to display different colors depending on viewing angle, often shifting between green, gold, and reddish-brown tones within the same crystal structure. However, this effect becomes most visible only after careful orientation during cutting, when the internal crystal axes can interact with light under controlled conditions. Before that moment, the transformation remains hidden. Unlike gemstones that signal their presence through immediate transparency or vivid saturation, Andalusite can appear visually restrained while still containing complex internal optical behavior. Its value does not rely on intensity of color alone, but on the dynamic way color changes as the stone is rotated. Historically, specimens have been collected as mineral curiosities rather than recognized as gem-quality material, partly because the optical performance of Andalusite depends heavily on how the crystal is oriented prior to cutting. Without that knowledge, rough fragments may appear comparatively uneventful. River transport further complicates recognition. Surface abrasion can obscure crystal faces that might otherwise indicate internal structure, making identification more dependent on careful observation rather than immediate visual impact. Once cut correctly, Andalusite reveals a layered color response that creates visual movement within the stone, an effect that can appear subtle at first glance, but becomes increasingly compelling with continued viewing. This transformation illustrates a broader pattern within gemology. Some gemstones are not overlooked because they lack value, but because their value only becomes visible after intentional intervention. Andalusite reminds observers that rarity does not always appear dramatic in its original state. Sometimes the most distinctive characteristics emerge only after the material has been given the opportunity to reveal what was already present beneath the surface. In environments shaped by water, time, and geological movement, that distinction is not always immediately obvious. Ranked 8th, Spinel. Long before advanced mineral testing became widely available, certain gemstones moved through history under incorrect names. Spinel was one of them. Across centuries, red Spinel crystals were repeatedly confused with ruby, appearing in royal collections and historic jewelry without distinction between the two materials. Only later did mineralogical analysis confirm that Spinel belongs to an entirely different crystal system, despite visual similarities when cut. In natural environments, however, Spinel often presents the opposite challenge. Instead of appearing too similar to another valuable gemstone, rough Spinel can appear too similar to nothing remarkable at all. When exposed to prolonged river transport, Spinel crystals may lose sharp crystal faces that would normally provide identification clues. Surface textures become smoother, edges soften. External color may appear darker or more muted due to weathering, mineral staining, or microscopic abrasion. Among gravel deposits composed of quartz fragments, feldspar pieces, and various silicate materials, Spinel can easily blend into the background. Without laboratory testing or cutting, its internal clarity and color saturation remain concealed beneath an exterior that offers little immediate visual contrast. In certain lighting conditions, rough Spinel may appear nearly indistinguishable from common river stones that share similar density and surface characteristics. The difficulty is compounded by the fact that Spinel forms in geological environments that often produce other visually similar minerals. Mixed deposits can contain multiple crystal fragments transported together through erosion, further reducing the likelihood that any single stone attracts immediate attention. Historically, this dual identity has shaped Spinel's unusual position in gemology. At times, it was mistaken for more famous gemstones. At other times, it was overlooked entirely. Its value was not always misunderstood in the same direction. Modern collectors increasingly recognize Spinel for its stability, clarity, and wide color range, including vivid reds, cobalt blues, and soft pastel tones. Yet in rough state, these qualities may not be apparent without examination under proper lighting and orientation. Spinel illustrates how classification plays a critical role in determining perceived importance. When a material lacks obvious visual signals associated with rarity, identification becomes dependent on knowledge rather than immediate appearance. In riverbeds where thousands of mineral fragments accumulate over time, that distinction can easily remain unnoticed. A stone that does not immediately attract attention may still possess properties that only become visible through closer study. Spinel's history demonstrates that recognition is not always a matter of visibility, but of understanding what is being observed. Ranked 7th, Grossular garnet, Savorite type rough. In several gem-producing regions, value is not determined only by what is found, but by what is expected to be found. Geological expectations shape attention. In areas dominated by quartz, feldspar, and common silicate minerals, local miners often develop a visual familiarity with the types of material most frequently encountered. Over time, this familiarity becomes a filtering mechanism. Stones that resemble common regional minerals may receive only brief consideration before being set aside in favor of specimens displaying more obvious color intensity or transparency. Certain varieties of Grossular garnet, including those capable of producing Savorit quality material, can initially fall within this visual blind spot. When transported through river systems, Grossular fragments often lose the sharp crystal geometry associated with freshly exposed mineral surfaces. Instead, water movement gradually rounds the material, creating pebble-like forms that visually integrate into surrounding sediment. Surface textures become less diagnostic. Edges soften. External color may appear uneven or partially concealed beneath mineral staining accumulated during transport. Within this context, the gemstone does not appear rare, it appears familiar. The geological environments that produce Grossular garnet are frequently associated with metamorphic processes involving calcium-rich rocks. These same environments may also yield visually similar minerals that occur in significantly greater abundance. Without visible transparency or strong color saturation in rough form, differentiation can require closer inspection than typical field conditions allow. Savorit quality Grossular garnet, known for its vivid green coloration once cut, does not always display its most desirable optical qualities before preparation. External layers may obscure the clarity and color consistency that become more apparent after careful examination. As a result, certain fragments may initially be grouped with more common greenish minerals present in the same region, especially when surface wear reduces visual contrast between specimens. Geographic familiarity can influence perception as strongly as the physical properties of the stone itself. When a location becomes associated with particular mineral types, attention may unconsciously prioritize those expectations, reducing the likelihood that visually subtle variations are investigated further. Only after cutting reveals internal transparency and color distribution does the distinction become more apparent. Grossular garnet demonstrates that rarity is sometimes overlooked not because it is invisible, but because it appears where observers are not actively expecting it to occur. In river systems shaped by long-term erosion, where countless fragments accumulate together, valuable material can remain hidden within patterns of familiarity that guide attention toward what is already known. Recognition in these cases depends on the willingness to question whether the expected geological narrative always reflects the full range of possibilities present in the environment. Ranked 6th, Sphene, Titanite. Under most natural lighting conditions, certain minerals remain visually quiet, not because they lack complexity, but because the conditions required to reveal that complexity are rarely present at the moment of discovery. Sphene, also known as Titanite, often exists within geological environments where erosion gradually releases fragments into surrounding sediment systems. As these fragments move through riverbeds, repeated contact with other stones can soften edges and reduce surface definition, creating shapes that resemble ordinary mineral debris rather than material associated with exceptional optical performance. At first glance, rough sphene does not typically display the brightness or transparency that might immediately signal gem potential. External coloration may appear subdued, often leaning toward earthy green, brown, or yellowish tones that visually merge with other silicate fragments present in the same environment. Yet Sphene possesses one of the most remarkable optical properties found in natural gemstones: extremely high dispersion. Dispersion refers to the ability of a material to separate white light into spectral colors. In properly cut sphene, this effect can produce flashes of color that exceed the intensity observed in many more widely recognized gemstones. The visual result is not simply brightness, but dynamic light separation that creates movement within the stone as viewing angles change. However, this behavior rarely becomes visible in rough form. Surface irregularities scatter incoming light in unpredictable directions, preventing the internal optical structure from interacting with light in a controlled manner. Without polished facets aligned to optimize light return, Dispersion remains largely hidden within the crystal's internal structure. River transport further masks identifying characteristics. As Sphene fragments travel downstream, abrasion can dull external surfaces and obscure crystal faces that might otherwise hint at internal optical potential. In mixed sediment deposits, visual distinction becomes increasingly difficult when multiple minerals share similar color ranges and surface textures. Because sphene is less commonly encountered than many silicate minerals found in alluvial environments, recognition often depends on familiarity with subtle indicators rather than immediate visual contrast. Only after cutting reveals the internal interaction between light and crystal structure does the gemstone's optical complexity become fully apparent. The transformation can appear disproportionate to the modest appearance of the original fragment. Sphene illustrates how certain gemstones remain overlooked, not because their properties are minor, but because those properties require precise conditions to become visible. When the defining characteristic of a mineral depends on the geometry of light interaction, the absence of polished surfaces can conceal qualities that would otherwise attract immediate attention. Within river systems shaped by constant motion, such characteristics may remain hidden until the material is examined in an environment designed to reveal what natural conditions do not immediately display. Ranked fifth, Grandidierite. For much of its documented existence, Grandidierite occupied a category rarely associated with widespread recognition, the museum mineral. Discovered in southern Madagascar in the early 20th century, Grandidierite was initially identified as a mineralogical curiosity rather than a gemstone suitable for cutting. Early specimens were typically opaque, often preserved as reference material for geological study rather than considered candidates for faceting. Because gem quality transparency was not immediately observed, the material remained largely confined to academic collections and institutional archives, where classification took precedence over commercial interest. In natural environments, Grandidierite does not always present characteristics that immediately suggest rarity. Rough fragments can display subdued bluish-green coloration that visually overlaps with a range of more common metamorphic minerals. Surface textures may appear uneven or granular, and without noticeable transparency, differentiation from surrounding material may require closer examination than field conditions typically allow. River transport can further obscure identifying features. As fragments move through sediment systems, abrasion gradually reduces sharp crystal boundaries, creating shapes that resemble ordinary mineral debris. Over time, the external appearance may lose many of the geometric indicators that might otherwise signal unusual internal structure. Because early discoveries did not immediately reveal transparent materials suitable for cutting, recognition of Grandidierite's gem potential developed gradually. Only after later findings demonstrated that certain crystals possessed sufficient clarity for faceting did broader interest begin to expand beyond academic circles. Even then, the gemstone remained relatively unfamiliar outside specialized collecting communities. Grandidierite's rarity is influenced by both geological scarcity and the limited number of locations capable of producing gem-quality material. Its formation requires specific conditions involving magnesium-rich environments and complex metamorphic processes that occur infrequently within the Earth's crust. Despite these constraints, the stone does not necessarily communicate its uncommon origin through obvious visual signals when encountered in rough form. The historical trajectory of Grandidierite reflects an unusual pattern. Recognition followed availability rather than the reverse. Instead of demand emerging immediately after discovery, awareness developed slowly as understanding of the material evolved through continued study. In river environments where countless mineral fragments accumulate over time, such stones may not attract immediate attention if their external characteristics appear consistent with more familiar materials. Grandidierite demonstrates how the perception of value can remain dormant when classification precedes aesthetic appreciation. Only after the possibility of transparency became widely documented did its position shift from mineral specimen to collectible gemstone. The material itself did not change. The understanding surrounding it did. Ranked fourth, Benitoite. Rarity is sometimes controlled not by appearance, but by geography. Certain minerals occur across multiple continents, forming in a wide range of geological environments. Others emerge only where highly specific conditions briefly align. pressure, chemistry, temperature, and time intersecting in ways that are difficult to replicate elsewhere. Benitoite belongs to the latter category. This barium-titanium silicate forms under a narrow set of geological circumstances, historically associated with a limited region of San Benito County, California. Within that locality, benitoite crystals developed inside hydrothermally altered rock formations, often embedded within a matrix that visually resembles other compact mineral assemblages present in the same environment. When fragments of host rock are transported by natural erosion into surrounding sediment systems, the external appearance rarely signals the presence of a rare gemstone within. The matrix material itself may appear dense, uneven, and visually similar to numerous other rock types commonly encountered in mineral-rich terrain. In rough state, benitoite crystals do not always display the vivid optical qualities that later become associated with the cut gemstone. Surface irregularities scatter incoming light, preventing the internal structure from demonstrating the strong brilliance and dispersion observed after faceting. Without careful cleaning or preparation, the visual distinction between benitoite-bearing material and more common geological fragments can remain subtle. Because benitoite originates from such a geographically restricted formation environment, its rarity is shaped not only by the number of crystals produced, but by the limited opportunity for new discoveries outside that original geological context. Unlike gemstones associated with extensive global deposits, the probability of encountering benitoite depends heavily on proximity to very specific geological conditions that occurred only under particular circumstances. When fragments are separated from their original host rock and exposed to erosional transport, identifying characteristics may become less obvious. Crystal faces can become partially obscured, and external coloration may appear muted until the stone is properly examined. The resulting visual ambiguity can contribute to delayed recognition, especially in environments where multiple mineral fragments share similar physical characteristics. Benitoite illustrates how geographic limitation can influence perception. A stone may appear visually consistent with its surroundings, yet remain exceptionally uncommon due to the rarity of the conditions required for its formation. In such cases, rarity is not immediately visible through surface observation alone. It exists within the geological history embedded in the material itself. Only when that context becomes understood does the distinction between common appearance and uncommon origin become fully apparent. Ranked third, Demantoid garnet. Among the many fragments carried through ancient river systems, rounded mineral nodules often accumulate with little visual distinction between them. Years of geological transport can soften crystal edges, polish surfaces through friction, and produce shapes that resemble ordinary pebbles scattered across sediment beds shaped by constant movement. Demantoid garnet frequently begins its visible journey in this form. Unlike gemstones that display immediate transparency in rough state, Demantoid may appear externally modest when first separated from host rock. Surface oxidation, mineral coatings, and abrasion can reduce the contrast between the stone and surrounding material. Under natural lighting conditions, its external appearance may not immediately communicate the optical complexity contained within its crystal structure. Yet Demantoid possesses an internal characteristic that distinguishes it from most other members of the garnet family: exceptionally high dispersion. Dispersion determines how strongly a gemstone separates white light into spectral colors. In well-cut Demantoid, this optical behavior produces flashes of green interwoven with spectral fire that can rival or exceed the intensity observed in stones more widely recognized for brilliance. In rough state, however, these optical properties remain largely concealed. Irregular external surfaces scatter incoming light unpredictably, preventing internal dispersion from becoming visually apparent. Without controlled facet geometry, the gemstone cannot direct light in ways that reveal its full optical performance. The visual transformation that occurs during cutting can therefore appear disproportionate relative to the original appearance of the material. Some Demantoid crystals also contain internal fibrous inclusions, known as horsetail inclusions, formed through mineral growth processes involving bassalite fibers. These inclusions, rather than reducing desirability, often serve as indicators of natural origin and contribute to collector interest. In river environments where mineral fragments accumulate together, nodular demantoid may resemble other rounded stones shaped by erosion. Differences in density, refractive behavior, and crystal structure remain invisible without examination beyond surface appearance. Because the gemstone's defining characteristics depend heavily on light interaction within precisely oriented facets, recognition rarely occurs at the moment of initial discovery. Demantoid demonstrates how visual performance can remain hidden when environmental conditions do not allow internal optical behavior to emerge. A stone capable of producing intense dispersion may initially appear subdued, simply because the geometry required to reveal its properties has not yet been created. Within dynamic sediment systems, where countless fragments share similar external textures, the distinction between common and uncommon material can remain unnoticed until structural preparation allows light to interact with the crystal as intended. Only then does the full complexity of the material become visible. Ranked second, Jeremejevite. Scarcity does not always correlate with visual intensity. Some of the rarest minerals known to science display only restrained coloration, minimal external contrast, and crystal habits that do not immediately differentiate them from far more common geological material. Jeremejevite belongs to this category of understated rarity, a mineral whose formation conditions are exceptionally limited, yet whose external appearance often remains quiet and unassuming. First identified in Siberia in the late 19th century, Jeremejevite forms through complex borate mineralization processes that require a precise combination of aluminum-rich environments and highly specific geochemical conditions. These circumstances occur infrequently, resulting in a distribution pattern that is notably restricted compared to more widely recognized gemstone species. In rough state, Jeremejevite commonly presents pale blue to colorless tones that can visually resemble quartz fragments or other transparent minerals frequently encountered in erosion-affected environments. Crystal surfaces may appear lightly frosted or slightly weathered after exposure to natural transport mechanisms, reducing the visual clarity that might otherwise distinguish the material during initial observation. Because river systems tend to concentrate minerals with similar density characteristics, Jeremejevite fragments can accumulate among visually comparable stones without obvious external markers indicating their rarity. Without prior familiarity with subtle crystal structure indicators, differentiation may require analytical methods rather than immediate visual recognition. Historically, only a limited number of gem-quality Jeremejevite specimens have been documented with sufficient transparency for faceting. Even within mineral collections, the species remained relatively obscure for extended periods due to the small number of confirmed localities capable of producing materials suitable for gemological use. The rarity of Jeremejevite is therefore not defined by dramatic appearance, but by the narrow geological circumstances necessary for its formation. Its value lies in probability rather than visual prominence. A mineral requiring highly specific environmental conditions may occur so infrequently that recognition becomes dependent on specialized knowledge rather than immediate aesthetic impact. In environments shaped by erosion and sediment transport, stones displaying minimal visual distinction may pass unnoticed simply because they do not trigger attention based on appearance alone. Jeremejevite demonstrates how extreme rarity can exist without dramatic visual signals. A gemstone may be uncommon not because it appears extraordinary at first glance, but because the geological pathway required for its creation occurs only under circumstances rarely repeated within the Earth's crust. Recognition in such cases depends less on visual intensity and more on understanding how unlikely the material is to exist at all. In first place, Painite. In mineralogy, there are moments when recognition arrives long after the material itself has existed. Painite represents one of the most striking examples of how rarity can remain unnoticed, not because the material lacks significance, but because the knowledge required to identify it has not yet caught up with its existence. Discovered in Myanmar during the 1950s, Painite was initially recorded as a mineral specimen rather than a gemstone of broader importance. For decades, only a very small number of crystals were confirmed, leading to its reputation as one of the rarest minerals known to science at the time. Yet the crystal itself did not visually communicate this status in any obvious way. In rough form, Painite often displays brownish to reddish tones that can appear relatively subdued compared to gemstones traditionally associated with vivid saturation or immediate brilliance. External surfaces may appear slightly uneven or modest in luster when observed under natural lighting conditions, particularly when the crystal remains embedded within matrix material or has experienced minor surface wear. Within geological environments containing multiple oxide minerals, visual differentiation can become challenging without detailed structural analysis. Painite's composition includes zirconium and boron within a complex crystal lattice, forming under conditions that occur only rarely in nature. Because these geochemical requirements intersect under very limited circumstances, the number of localities capable of producing the mineral remains small relative to more abundant gemstone species. For many years following its initial identification, additional discoveries were extremely limited. The rarity of confirmed specimens contributed to increasing scientific interest in understanding the processes responsible for its formation. Despite this scarcity, the external appearance of rough painite does not immediately suggest an extraordinary origin when encountered without context. Like many minerals formed under specialized geological conditions, its defining characteristics exist primarily within internal structure rather than external visual intensity. Recognition therefore depended on analytical observation rather than immediate visual distinction. Painite illustrates how perception of rarity evolves as knowledge expands. A mineral may exist for extended periods without widespread awareness of its significance, particularly when its outward characteristics do not strongly differentiate it from surrounding material. Only after careful study reveals the unusual combination of chemical composition and crystal structure does its position within the hierarchy of rarity become fully understood. Within river systems in erosion-affected environments, stones shaped by geological time often present themselves without explanation. Painite demonstrates that the most exceptional materials do not always appear exceptional when first encountered. Sometimes the distinction between ordinary and extraordinary exists not in outward appearance, but in the improbable sequence of conditions required for the material to form at all. Recognition in these cases becomes an evolving process, one that develops as understanding of the natural world continues to expand. Rarity does not always announce itself. Some of the most valuable gemstones ever discovered did not stand out at the moment they were first seen. No dramatic brilliance, no obvious signal, nothing to separate them from the countless ordinary stones shaped by erosion and time. Only later did their internal structure reveal what their surface concealed. Complex chemistry, uncommon formation conditions, optical behavior invisible until examined more closely. These gemstones challenge one of the most persistent assumptions in collecting, that rarity should always look rare. In reality, some of the most exceptional minerals appear visually quiet, their significance defined not by immediate appearance, but by how unlikely their formation truly is. Understanding this difference changes the way geological discoveries are interpreted, because the next overlooked stone may not appear extraordinary at first glance, yet still contain a structure formed under conditions that rarely occur within the Earth's crust. And sometimes what appears ordinary is simply waiting for the right moment to be understood.